everyone. And if I may continue, also very warm greetings from me and my colleague Markus Staub. We're continuing with a humble presentation and some videos, hoping to give you some vivid insight how the e-highway near Frankfurt actually looks like, followed by a short presentation from both of us on the system itself, its potential, and yeah, also giving you an outlook of what we think which might be possible for the next steps to be expected in the near-time future. Then my colleague Markus Staub will give you also some insights on norming and standardization aspects, and we close our contribution by showing you or to give you some more impressions on the driving experience by one of the drivers who has most of the experience shared so far or given so far in this very project of ELISA. Well, as I said, let's start with the key here, which is the infrastructure. I hope you can see my screen by now.
Yeah, we can see it.
All right. So as we can see here, this is an aerial view of the electrified section on the motorway A5. And as Dr. Reuswig already explained, this is one of Germany's most dense or most frequented motorways we have. It's connecting the southwest part of Germany through the Scandinavian freight corridor. So it's a really essential and core road freight network for Germany and also neighboring countries. And this 5-kilometer stretch was built before last year. And as you can see here, it has got 4 lanes in each driving direction. It's very close to Frankfurt Airport, and it's connecting logistic hubs near the Frankfurt Airport and some other logistics hubs, and as well as manufacturing plants down south in the direction of Darmstadt. If we close a little bit more here, you can see how it actually looks like. So this is the entering section of the e-highway with some trucks equipped with pantographs now passing in and just connecting to it. So this is already daily routine. So this is not only testing and demonstrating as it works, it really is part of the daily operation of the freight forwarding companies using those trucks there. And the experience so far, we're expecting some more scientific reports in the next months to come. These will be published by the Technical University of Darmstadt and partners. And it's not only about the technical aspects, so how many miles were driven, what is the electrical share or proportion of electrical drive in the overall mileage. It is also covering aspects like what is the potential influence of such an infrastructure on the motorways to other users of this motorway section. And this will be, of course, very interesting to see and to learn what the results are. We see here part of the infrastructure like part of the catenary, here a pole, and we have in this section all over more than 200 poles erected.
All right. Hello, everyone. Marcus speaking. Now we're going to the power substation. You can see one of our experts. This is inside a power substation, a control panel. At the moment, what we see is the electrical interface, and you can, of course, also review the switching status of all the switches inside the power substations. You can switch from the power substation, but also, of course, from the traffic management control center that Dr. Reuswig mentioned before. So yeah, as I've said, this is a picture from inside of the power substation. This is a little bit zoomed out. Yeah, from my point of view, there were critics that infrastructure doesn't blend in all too well with the landscape. Well, I say it's of course a matter of taste, but on the other hand side, well, the highways aren't the most beautiful places on earth, to be honest. But that's just a side comment. So we are now coming to Yes, this is also a view from the side. You have the electrified highway section on the left side.
And also, which is not to be seen here, is we have some crossing transmission lines from the grid, and we also had to incorporate this kind of transmission lines there without any trouble.
Yeah, exactly. By the way, the white things that are swinging, these are bird deflectors. Yeah. What you see over here on the right-hand side, this is a so-called semi-inclined catenary type, which was designed to fit really good with the curve, with the bend of the road, so that contact line is always straight over the middle of the road. And yes, the construction itself, apart from that you have two catenaries, is mainly built up of standard railway components. So you also have a contact line, which is in physical contact with the pantograph. You have a messenger wire. You have droppers in between. You have more or less standard poles, and you have cantilevers, which are attached to the poles and are supporting with via steady arms the whole structure. So what you see over here on the right-hand side, these are poles with tensioning devices. Also with reference to the railway, these tensioning devices are meant to keep or to maintain an exact tensioning force inside of the two wires, so that there's no sag in the wires. So this is another view on one of the standard poles. The additional line that you now see here on the cantilever, by the way, that's an earth wire. But yeah, maybe we're going to talk about this later on. So this is also a zoomed-in view. Now we're going to talk about some special designs. There were some questions about bridges, and we're going to show you now how we electrified a bridge. So just to give you some estimates, this bridge has a height of 4.82 meters, and the contact wire, which was lowered for this specific case, is at 4.57. So basically for the vehicle, it doesn't make any difference. It just passes right through. The pantograph's going a little bit down, it passes the bridge, and afterwards it's going up again to the nominal height. And we also attached the steady arms which hold the wires with standard railway components just right to the bridge structure. Okay. These are now some moving pictures to the traffic control center that Dr. Reuswig has already mentioned at Hessen Mobil. From there on, the whole traffic is controlled, and of course also is the e-highway infrastructure. So this is now a more detailed view on one of the two of the contact strips of the pantograph. You can see the contact wire, which is the thick wire on the left, wasn't in the middle of the pantograph. No worries. So this is a display which is inside the driver's cabin, which enables the driver to have a look on the pantograph to see if it's raised or not. But this is just additionally. Of course, he also has some indications in his display right in front of him. This is another way of transmitting the video signal from the pan to the driver. So this is the standard media interface from Scania. And then you can switch between having a look at the pantograph or going to the radio, for example. But under normal operation, there's no need for the driver to have a close look on the pantograph. This is just for you, of course, to give you nice moving pictures, and also if the driver is interested in it. So what we now see is a connection process, I think. So at the moment he's still lowered. Now the driver, I think, soon is going to push the button. Yes, he does. Well, the pantograph raises, it connects, and that's all the magic. And from now on, we're driving fully electric.
While recharging the batteries, of course, yeah.
And of course, yes.
So using our experience from railway industries, we are able to provide maximum speed of up to 100 kilometers an hour. So this is sufficient, I think, for the usage for such kind of trucks on motorways.
Yeah, exactly. As Mr. Thoren from Scania has mentioned before, there are several ways or several options when the pantograph is lowered. Two have already been mentioned, when the pantograph leaves the OCL zone or when the vehicle itself leaves the lane. There's also a third option, being that at the end of the e-highway track, the contact wire is going up. This is detected by the pantograph, and when a certain limit is reached, it's also lowering automatically.
All right. Some more insights on the truck and how it feels and looks like. We're going to give you in a few minutes time. We would like now to switch to our presentation we've prepared for you. I'm still audible, right?
Yes, you're audible and we can see your presentation.
All right. All right, thanks. So as of 2020, we have, let's say, seen some daily operations on both motorways in Germany. As it's displayed in here, we used in real operation transports, and by the use and based on a existing truck platform. And this, let's say, has not started just yesterday, I would say. Krista already told, well, this was eventually already tried out in the 19th century, which might be precisely the case for this kind of carriage fed by electrical power from a catenary or so-called catenary or pre-early catenary design. We started our basic thinkings in 2010, so almost 10 years ago now from today. Thinking and concepting a first generation of trucks and pantograph or collector for those kind of trucks on our home-based field, or how shall I say, research and development section near Berlin, which is a former military air force field from used by the Soviet armed forces in all the years. And on this trip, we transformed the former airstrip into a German autobahn, you can say, with all the elements which a normal autobahn or motorway has to offer, except for a bridge maybe. And with this kind of testing field near Berlin, we used to trial out several stages up to the present day, having the third generation of pantograph and the newest version of the Scania hybrid truck you see on the right-hand side of this presentation. And we think we've now, let's say, developed, or we reached a maturity stage of this kind of technology. We don't have, let's say, any great limitations on the first and last miles, thanks to the hybrid concept of these kind of trucks, and which offers the greatest level of flexibility. We have also made several testings and concepts and tried them out in reality, which are seen here in a colored way. And the only few exceptions we haven't tried out so far is a fuel cell truck running at the catenary line, but we hope to see this kind of hybrid to be seen and realized in a very near-term future. And as it was already pointed and explained by Julius Jörns from EVA Institute, why do we think this e-highway system is of a great use and benefit for the future of road freight transport on motorways specifically? This is answered by this kind of display by the Öko Institute, which makes a very vivid impression on what are the key elements which lead to a very different output in terms of efficiency. And efficiency, of course, is key to everyone, which is not only investing into the infrastructure, but into the trucks, into the vehicles, and operate themselves in order to earn money. So efficiency is it. And this was also based by a similar finding by the ICCT, comparing the different blocks of cost, you could say, from the infrastructure, from the energy perspective, and also from the vehicle itself. And if you combine this between the electric, meaning here the overhead catenary solution, the LNG, and the today's combustion power to liquid engines, and the fuel cell, not to forget, it's getting quite clear that it's not really the infrastructure costs which matters, but it's all about the energy over the life cycle of such trucks. And therefore, we think that e-highway is really a backbone for the future demand-oriented drive mix on motorways, not only in Germany. So the catenary lines are some sort of a basic backbone, and this can be combined with other drivetrains and fuel technologies, such as the battery, which we see nowadays in urban and regional transport already. So this is already there, this technology. It can be combined with e-highway. And then we, of course, can also implement and fuel cell-based trucks on non-electrified sections, which need a greater range, for example, on sections where an electrification wouldn't make much sense because they are not that frequented. And then not to forget, of course, by 2030, we will be seeing still a large number of trucks with internal combustion engines. And also for those trucks, we need a solution. And this also can be combined with the e-highway. So as I said, direct use of electrical energy is key because of its high efficiency. And this makes the overall e-highway system the most economical and sustainable solution. How might be the further next steps could look like? Well, we think that after having those field trials on this conceptual tests and demonstration projects seen in the US and Sweden and now in Germany on those three different sections, it's time to further develop and to implement pilots. So to see that it really works and commercially viable is for the usage at fleet scale. And this could be, let's say, starting with a track length of 20 kilometers or more up to 100 kilometers. So it can be scaled up very quickly or in short time, providing as many trucks as possible. And then we surely definitely will see that there will be a great benefit to everyone using such a system. And it's really possible to mount up or to scale up catenary. We have seen this in Germany. This is in the middle of my presentation slide here. There had been between 1955 and 1965 a great deal of catenary installation seen on Germany's railway system. So many thousand kilometers within this 10 years of time. So this was already possible more than 50 years ago, and we are convinced that this is possible for the future and can be replicated on motorways as well. In many studies, at least in Germany, there also had been some hints how this can be then linked not only to a national solution in Germany. There are strong indications that even an island solution for Germany alone would be economically sensible and viable, but it makes, of course, in terms of saving and abating CO2 emissions in Europe, even more vital to combine this system with the neighboring countries or to grow it up to a European-wide system. And this is also displayed on this next slide here. We see great interest, not only in Europe, but also from outside Europe, like in India, China, and the US, and such a solution. And more specific in Sweden, we see there that the government there plans to build 1,500 kilometers of electric highways by 2022, not necessarily the e-highway system, but we're talking about electric road systems. Then, of course, in the UK, we see some promising thoughts and initial concepts rising in the north of England, which we hope to hear later from David Sibon. Then in Germany, as we've already seen, we have got 3 field trials. Even in Hungary, the Minister for Transport is considering e-highway on 2 potential sections on motorways. And last but not least, for Austria, we also see that the current government also incorporated this kind of solution in its governmental program. And for the rest of Europe, we see also strong indications that in terms of research and development funding, studies and initial thoughts and concepts are on the way. Now we would like to switch over again to my colleague, Markus Staub, who will give you some more insights on the infrastructure and how it was incorporated into the existing infrastructure on the motorways, and also giving some insights on the standardization and norming work he has done.
All right, thank you very much, Garrett. My name is Markus Staub. I'm also from the e-highway team from the engineering department. And I'm going to give you some brief details on the technical aspects of the e-highway system. So what you see here on the right-hand side in the picture is more or less the standard e-highway design. Of course, you have a pole attached to it, the cantilever for the mechanical support. The cantilever holds a so-called suspension column or suspension pillar. This is the thing going down. And attached to it are 2 steady arms, which hold the contact wire in position. You, of course, also see a retentioning device, which I've mentioned earlier. Yes, some key aspects on the system, and in this case, I think it's for the whole system. So the overall power distribution for the e-highway system is usually done on the medium voltage network. So this is a voltage level of about 10 to 30 kV. And at the moment, and I want to press this point, at the moment, the in-feed voltage of the substations to the vehicle on the DC side is on a voltage level of 670 volts. But I think I'm not going to spoil too much when I say that this is not going to stand for too long. We are already working on a much higher voltage level, and also, of course, talking to the vehicle side. Coming back, the in-feed from the substation to the electrified section, so from the substation to the pole where the electricity is actually in-feeded, is in this case done by underground cables, which are just put alongside the highway. And of course, and this is a question that I usually ask my students, why do we have 2 contact lines? It's similar to a tramway. The tram has only 1. And the clever students answer then, well, the tramway has a rail, of course, which is the return conductor, which we don't have. So that's why we need 2 contact lines, a positive and a negative one. Yes, we also have the retentioning device. And yes, the supply of the track components is also done via suspension cable. And we also have a so-called monitoring for the contact wire, or let's call it the contact wire monitoring system, CMS. This is a specific solution that we developed, and what it does is that it's attached to the tensioning wheel lever of the tensioning device. And it basically just detects the tensioning force inside the wires, inside the contact wire and the messenger wire. And if it detects any change of force of the tension conductors, which could be due to the unlikely case of a break of the contact wire, or for example, a tree is falling inside or anything else, this of course is from the side of the measurement device a certain force in the tensioning force. And this change is detected, and then we know, okay, there's something wrong, and it automatically switches off the electricity from the wire. All right, and these are just two pictures from the pole, which I mentioned before, from the in-feed pole. So you see on the left-hand side a big switch sitting attached to the mast. Then you have some black big cables which come from the ground, go up the mast, then alongside the cantilever to the right picture. And then you have some clamps. And over this clamp, the black cables transmit the electric power inside the contact wires. All right, these are some key figures for the e-highway project in Hesse, which we have been talking about today. So on the right-hand side is a short map. You have two power substations. Both of them are situated on already existing service stations. And as you can see, they mostly look like standard sea containers. The distance in between these power substations is roughly 2.5, almost 3 kilometers at the moment. Yeah, and on the left-hand side, you have some parameters. So in this case, the medium voltage network grid, public grid, we are attaching to is 20 kV. Yeah, as mentioned before, the DC voltage is 670 volts now, and the power substations have a nominal power of 1 megawatt volt ampere. Yes, just to give you an overview, recently we had a test drive on the test track, and we managed to operate 7 trucks without any interference from the infrastructure side. Yes. We have 5 kilometers electrified sections in each driving direction, making it 10 kilometers in total. And for this project, there had to be 223 masts or poles being erected, plus 6 poles to be erected in the middle strip. That's what you can see in the centered picture below service station. Yeah, exactly. Yeah, so this is also a specialized solution that we were able to fulfill. I already had talked about bridges, and we saw a solution to go under bridges in the video. This is another solution which we have implemented in the second field trial in Schleswig-Holstein, so between Hamburg and Lübeck. So what you see here is basically a rigid rail or a conductor rail, and the 2 supporting points which hold this rigid rail are also directly attached to the bridge. Yes, and this was due to the fact that we were not allowed to attach anything to the middle of the bridge. So we came up with this solution, and it works quite well. All right, this is also a special feature I've mentioned before. This is a so-called inclined catenary section or catenary design. This is, or we need this because, of course, on highways you have bands with certain radiuses, and we want to have the contact wire or the middle between the 2 contact wires almost directly in the middle above the road, because this makes it much easier for the vehicle. So therefore we kind of have to curve or to bend the contact wire, and also as a reference to the railway, that's why we designed this so-called inclined catenary design. All right, these were just some technical elements, but there's another part which is also really important from my side, because parallel to the technical development, we are also really pushing and thriving on the project of standardization, because we don't want e-highway to work just in Germany and then kind of build it on an island, but as my colleague just mentioned before, we want this to be interconnected to our partners because traffic is also interconnected. So interoperability and standardization excuse me, is really important for us. So my next slides are going to be about standardization. And so what you see over here are just some aspects that we are working on and setting on standards. So you have on the left-hand side the vehicle. So of course, traction voltage and traction quality, etc., and everything about the pantograph is key in this term when it comes to setting standards for the vehicle. And of course, you also have to adapt and sometimes set certain standards for the electrical protection requirements and also EMC. On the infrastructural side, of course, the traction voltage and also tolerances and quality are really important. But you also have to define certain standard parameters when it comes to the geometry of the overhead contact line. And of course, also when it comes to protection and integration into public power networks. So what we did, and as you can see from the little bit funny looking e-highway truck, this is, I think, 8 years old, but still valid. In the really first step, we had a look on the whole system. We divided it into two main systems, being the infrastructure and the vehicle. And then we are trying to define interfaces between following subsystems. And so these interfaces are for us the starting point when it comes to standardization. So for example, you have interface number 3 being the connection point between the infrastructure, mainly the contact line, and the vehicle, in this part, the pantograph. Okay. All right, on the left-hand side, you find again the mentioned interfaces, and the right picture is meant to give you an overview where we are active at the moment. So the right picture is a brief overview about the whole world, let's call it like that, of standardization. So you have different levels. You have the international level, the regional level, and the national level. And we are active, as you can see, not just in the electrical world, being the IEC, the Senelec, and the PKE on German level, but also aiming on the ISO world and the general norming world. Okay. And now I'd like to give you some concrete examples, what we have done and what we're actually working on. So our process of getting the e-highway into standardization, as you can imagine, is a really long process because standardization takes a lot of time. And so we have two key documents or two key elements for this standardization process, one being a basic design criteria. And in this BDC document, we have defined relevant parameters and design criteria for the construction and operation of e-highway system. For example, ice loads and in which standard there's a reference to ice load and which value do we need or do we find acceptable for the e-highway system. So this is one of the key documents. The other one being a so-called standard and regulation roadmap. So me and my predecessors have picked up a lot of standards, not just from the Senelec and ISO, but also from OEMs or Siemens guidelines, etc. And they have had a look at them and checked, are they applicable to the e-highway? Are they especially not applicable to the e-highway? Is this something that we want to go into? Is this a standard that we want to implement in e-highway into? Is this a standard where we, for example, want to change something due to the e-highway? So we have a set roadmap, how we want to bring the e-highway from Siemens perspective into standardization. And this is really an open process. So To give you an example, we are talking on a regular basis, so 1 or 2 times a year, with the contact persons in the relevant standardization committees. And whenever they, for example, tell us, yes, this standard is revisioned or this standard is opening up again, we are checking it. We're having a look in our roadmap and saying, oh yeah, that's a good one. We'd like to change this. We'd like to update this standard. Yeah, so this is what our daily standardization road looks like. Then there's Fenelec working group, which is where Siemens is in lead, but there are also many other experts from other companies, such as OEMs or Alstom, for example, or pantograph manufacturers, etc. We are all working together on setting a new technical standard. This technical standard is going to have the title Technical Criteria for the Interaction between Pantograph and Overhead Contact Lines on Electrified Roads. So this is going to be, I think, the first pure e-highway standard that we are going to set, and we're making great progress. So we have first draft already revisioned, and now we're collecting the feedback and going into the second draft. And there's also a fourth example that I want to show you. Coming from the railway world, there's the standard 50119. And this also describes some specific about the contact line. And in this annex, when it's published this year, there's a new Annex C. And this Annex C describes specifications for overhead contact lines for electric trucks. So this is also a result of our ongoing work on standardization. And this is one of the first results. All right. Now a big step back. This is a detailed picture of the pantograph of the 3rd generation, probably not the last generation. You see some key features that our pantograph has at the moment. Number 1 being pantograph features an automatic brake detection system. So whenever there are some mechanical faults, for example, with the carbon strip, this is detected automatically and the pantograph is lowered and of course gives you a warning. If you think back to the first slides from Garrett, you may remember that the first pantograph of the 1st and 2nd generation were single arm pantographs, and this one being now a dual arm construction. And this is mainly due to an optimized force balancing between the contact forces of the 2 contact lines. Some other features, for example, are number 3, we have an inner horn detection. This is relevant when, for example, there's a really quick, or when the driver leaves the lane really quick to one side. So, and this prohibits the pan from coming in contact with the wrong contact line. All right. Okay, I think.
So, ladies and gentlemen, we have, let's say, finished our presentation, Marcus and me, and again, we would like to express our saying sorry. Let's say we haven't met. Let's say I could not meet in Frankfurt today, and could not, let's say, give you a real driving experience also on the trucks, not only showing that, but some of you at least could have the chance to sit next to the drivers, for test drivers, and also of some of the drivers working for the freight forwarding companies there. Everything was arranged, and we were thinking how to overcome this dilemma for this meeting and for this event. We thought about to show you something right from the truck, also giving some sort of words to one of the gentlemen who has one of the most driving experience with this Hypertruck, Mr. Schmieder from Schanz. And I would like now to start our last video and to close our contribution for that moment. So allow me please to change over again to this interview. And there we go. If there's anything wrong with the tone, please let me know.
Also ich sehe eigentlich fast jeden Tag einen Sonnenaufgang. Ich fange 4:30 an. fahre hier täglich von Oberramstadt nach Frankfurt-Fechenheim und auf der Strecke auf der A5 befindet sich die E-Highway-Teststrecke, die ich dann natürlich auch täglich benutze. Ich bin Thomas Schmieder, bin bei der Firma Schanz angestellt als Lkw-Fahrer und habe mich speziell für diesen Oberleitungs-Lkw in dem Projekt ELISA beworben. Wie man sieht, ist der Radstand etwas länger, weil A, eine Batterie verbaut ist an dem Oberleitungs-Lkw und B, natürlich Platz gebraucht wird für diesen Aufbau, wo oben drauf dann der Schwungabnehmer verbaut ist. Der fährt dann aus an die Oberleitung, in den Bereichen, wo die Oberleitung ist natürlich. Und dann hat man halt hier runter zu geht dann Batterie und Antriebsstrang. Ist halt der Elektromotor ist zwischen Motor und Getriebe gekoppelt. Das ist eine klare Einsprachung, weil man natürlich rein elektrisch fahren kann und dadurch den CO2-Emissionen und Dieselverbrauch natürlich senkt. Also wenn ich jetzt überholen muss, kann ich entweder durch einen Knopfdruck den Pantographen einholen oder durchs Blinker setzen. Nach links ist auch ein Signal, dass der Spurabnehmer einfährt. Überholen, rechts wieder einscheren. Einen Moment warten, bis der Spurhalteassistent die Spur wieder gefunden hat. Stromabnehmer ausfahren, weiterfahren. Der Spurhalteassistent, der jetzt in Lenkung mit eingreift jetzt, ist natürlich, sag ich mal, der Vorteil, dass man dann durch die Spur noch leichter oder noch exakter unter der Oberleitung halten kann. Ja. Also das ist schon, sag ich mal, sehr imposant, die Kraftentfaltung bei LKW. Wenn du durch von ersten Moment gleich 1200 Newtonmeter von Elektromotor mitschieben, ist es eine ganz andere Hausnummer, als wenn du rein mit dem Diesel-LKW anfährst. Der unterstützt sich beim Berghochfahren, der Elektromotor, auch voll beladen, fällt man am Berg kaum ab. Also muss ich sagen, das ist echt beeindruckend. Das sind so die Leistungswerte von dem LKW. Und ich sag mal, einen neuen Fahrer auf dem System zu lernen, eine Woche. Und dann kann man das System einwandfrei auch jeder andere bedienen. Ich würde mich freuen, wenn das Projekt in die Realität oder in das Straßennetz eingebunden wird. Das Straßennetz in Deutschland bietet sich ja sehr gut an. Ich freue mich jeden Tag in den LKW zu steigen und mit diesem LKW zu fahren.
That was great, Garrett. Thank you very much. And great to finish on an inspiring video like that with words of somebody who's actually involved on a day-to-day basis in driving trucks up and down the system. So thank you very much for that.